Okay, now we're going to look at the derivatives of the inverse hyperbolic functions. A few moments ago, we just derived the meaning of inverse hyperbolic, the one with natural log, x plus the square root of, etc. We just looked at why that formula was true. And now finally, I think you're going to start to see the end of the tunnel here. The end of the tunnel is, if these are the derivatives of hyperbolic inverse functions, now think about integrating the right-hand sides. Like say you want to find the integral of 1 over the square root of 1 plus x squared. Guess what it's going to be? It's going to be hyperbolic inverse sine function, right? What if you want to find the integral of this quantity? If you want to find the integral of this quantity, guess what that's going to be? Hyperbolic cosine inverse, of course. Say you want to find the integral of this quantity. That's going to be hyperbolic tangent. So the derivatives are useful, but you're going to see that these are mostly used for the integrals. Okay, we're going to show just one of these once again. And in just a little bit, once I give you the integral formulas, we're actually going to do a few examples as to how you can use those as integrals. And believe it or not, you may have never seen this before, but in your graphing calculators, these functions are there, these hyperbolic inverse, these mysterious functions. I had to look a little bit hard this morning. I couldn't find it easily, but I went under, you have a catalog. There is a catalog command. I'll tell you where catalog is. Second 0. Second function 0 opens the catalog command. And then if you want like sine hyperbolic, just press the letter S. I'm going to show you. We're going to use those in a little bit, but let me just give you the preview where they are located in your calculators. By the way, the catalog is really good to know. If you ever forget what was the command, or where can I find it, everything is listed in your catalog, no matter what other menus they may be involved in. They're also going to be in the catalog, and you can always invoke or get your command from there as well. So I'm going to go to, just to show you, go to second 0, opens the catalog menu. Before pressing any other key, because it's a very long list, you don't want to scroll down, just press the letter. It's automatically in the right mode to press the letter. What letter are we looking at right now? Say sine hyperbolic inverse, letter S. Letter S shares the same key as, you're right, natural log function. Just press that. Brings you to the S's. Come on down now. Interesting. Set date. I didn't know that was in there. Set time. All right. Keep going. Keep going. Go to the sines. Okay, sine inverses are the real trig functions. And the fake ones are the hyperbolic sine and hyperbolic sine inverse. They're in there. So if you ever want to find hyperbolic sine of a value, how would you bring it up? Say I want hyperbolic sine of something. Say 2. Basically, it's going to plug 2 in x in the definition of this e to the x definition of hyperbolic sine, and it's going to give you an answer. Right? So they're in there, and we're going to use one in a little bit. So we want to prove the first one. Okay, I don't want to just prove the first one. I'm going to copy and paste it to my next page. Okay, let's do copy and paste. Okay, I can get rid of the second part. Okay, so how are we going to prove this? Let's start with the left-hand side. Starting with the derivative of sine hyperbolic inverse of x. Okay, if we're going to prove something, we need its definition. What was the definition of the hyperbolic sine function? That's the one we spent a lot of time proving a few minutes ago. If you wrote it down, the result, can you please bring it back? Remember, that's the one with the natural log function in it. Natural log of plus 1. Thank you. Okay. We want to show that the derivative of this is equal to the right-hand side here. Okay. How do you find the derivative of natural log of something? Think of this as natural log of u. What is the derivative of natural log of u? Now, this little part by itself is a good review question for the final. We're reviewing what is the natural log of u, where u is a function of x. How do we find the derivative of something like that? What did you say? 1 over u times u prime. Let's remind everybody. So if you have natural log of u, and you're trying to find the derivative of that, it's going to be 1 over u times u prime, correct? Okay, for this question, what is my 1 over u going to be? 1 over everything, right? And then times the derivative of everything. We're trying to prove this identity, that the derivative of hyperbolic inverse sine is 1 over the square root of 1 plus x squared. Yes, because the definition of hyperbolic sine, a few moments ago, we got the definition of that was equal to this, correct? If you like, let's go back to that page and see that one. You remember that? Okay. Exactly. First, we wrote down the definition, and now we're going to differentiate it. Okay? To differentiate anything that has a natural log in it, we're using this rule, 1 over u times u prime, right? If you have like natural log of u, the derivative is 1 over u times u prime. So far, I have the 1 over u part. Okay, but what should I write for the u prime part? This is going to be a little bit messy now. What is u prime going to be? What is the derivative of this inside part going to be? Derivative of x is 1. Okay, what about the derivative of this quantity? Who can tell me a quick answer? Let me see how quickly you can do this. It's good to know the derivative of root x. Does anybody know the derivative of just root x? It's 1 over 2 root x. Okay, it's good to know that for quickness purposes, like as you go on in Calc 2. But if you have another quantity like this, it's going to be 1 over 2 times that quantity. But from the chain rule, you also have to multiply it by what? By 2x. Now, that was a quick way to do it. Let me also show you the regular, slow way, which is you first write it like this. Correct? You bring the 1/2 down, subtract 1 from the power, multiply everything by the derivative inside. But if you do all that, you're going to get this answer that we got here. I'm going to write that answer. Okay, we want to simplify this. What are we trying to show? That this quantity is the same as the right-hand side. We're trying to show this huge mess is going to simplify and show us that it's the same thing as the right-hand side. Any thoughts what we could do here to simplify that mess? Again, there's a multitude of things we could try to do. We could get a single denominator. Also, we could try to distribute this quantity. Like, oops, looking for the undo key here. Okay, so say you could do this times this, and this times that, right? So let's do so. This times 1, you get the same thing back. And then this times the second one, I need to multiply the bottoms. What am I missing on the bottom? I'm multiplying this with the second term. On the top you have an x. On the bottom, basically you have this quantity times what? So what should I be multiplying it with? Exactly. Because I'm multiplying the two bottoms together. This one, I'm multiplying it with that bottom. Okay, to get common denominators, what should I multiply the first fraction, top and bottom, with? They both have this in them, right? So the first top and bottom should be multiplied by what? Under a radical, right? Yes, multiply top and bottom by radical x squared plus 1. And then write as a single denominator. Now that we have the same common denominator, and the common denominator is now I'm going to let you guys look at this for a minute, see if you see a simplification here. Yes, Daniel?
Split them up and cancel the radical x squared plus 1 over radical.
No, but then we're going backwards. Then we're going to get the two fractions again. Instead of splitting, any other thoughts? This entire top can be canceled with this entire parentheses bottom, right? Because it's just a different order. Like think of it a plus b, and then this is b plus a. But this is really the same thing as that, correct? And you know, sometimes when you do proofs, you're allowed to cheat a little bit. I always do this. Okay, if I'm going to be proving something, I look at what is my end result supposed to look like, and see if you can see that within your expression. Like what were we trying to prove? We were trying to prove that the right-hand side was 1 over the square root of 1 plus x squared. So I knew we had to keep this on the bottom. And again, if you cancel this with that, you're going to be left with what you're trying to prove. So it's always helpful to look at the right-hand side to see, okay, what are we trying to prove? And do we already have it, or do we have to simplify it further, and so forth? Okay, do we have the proof then? Do you then agree that the derivative of hyperbolic sine inverse is 1 over the square root of 1 plus x squared? Okay, finally I can deliver the promise I had earlier today. I said to you guys, we're going to be able to integrate something like this by the end of the class today. So do we know the answer to this right now? Because if the derivative of hyperbolic sine inverse is 1 over the square root of 1 plus x squared, then the integral of that 1 over square root of 1 plus x squared is what? Let me try to keep them both on the same page if I can, so you can see and cheat. So the answer will be here. I will even do it a little bit easier for you. I'm going to clone the page and get rid of all the extras in the middle. And put that closer up with that formula. Okay, so now we can see both of them easily, right? Get rid of the clutter a little bit. Oh no. Okay. Yeah, let me just put that by hand. What was the bottom? 1 plus x squared on the bottom, right? Okay. Okay, so if the derivative, you have the equation in front of you. Now I'm asking you, what is the integral of 1 over the square root of 1 plus x squared? And your answer is hyperbolic sine inverse of x plus c. Okay. Could you have done this question with u substitution? Could you have integrated this using u sub? No, there is no x on the top, right? Could you have used regular inverse sine function? No, because you don't have a minus on the bottom, right? So you don't have that. So you had to use something different, and that something different is hyperbolic, the sine hyperbolic inverse function. Okay, going back to those three formulas. So I only proved one of them. I'm not going to prove the other ones. I don't need to confuse you any more than I have to today. So these are the three derivatives. Okay, with these three derivatives, then do you know the answers for three integrals? Like if I integrate this, you know what the answer will be, right? The answer will be that, right? If I integrate this, the answer will be sine hyperbolic. If I integrate this, the answer will be cosine hyperbolic. Now let me get rid of those. So I'm going to write those separately, but I just want you to see them clearly. Okay, so this is what they look like. The integral formulas look like the following. But I already told you those, right? I already told you them. So this is nothing new. But just like in inverse trig functions, sometimes instead of a 1, what do they have? Like an a or a square, right? So therefore, they have the extended formulas. If there's an a instead of the 1, this is what the formulas turn out to be, just like the inverse trig functions. The tangent has the 1 over a in it. The other ones don't have the 1 over a in it. And with that, we're going to be able to do a few examples. And here's the first example right here for you guys to look at. This one. Look at the problem, see which formula applies, decide what your a is, and write the answer, basically. So this one follows the pattern. Remember, your a is your constant. Your x is your variable. In this case, what is our a for this question? A is the square root of 3, right? Because a squared is 3. And which of these three are you going to use? This, or that? Let's say column 1, 2, 3. Number 1, right? So you have a sum of two squares, or you can regard it as sum of two squares under a radical. So it's going to be the first formula. So tell me your antiderivative, please. Hyperbolic sine inverse of x over radical 3. Very good. And the limits are from 0 to 1. So we need to know what is this function at 1 over radical 3 minus this function at 0. And this is where the calculator command will be helpful. I had the sign hyperbolic on the screen. I need the inverse one. So I'm going to go back to that second 0 opens the catalog. Then just press the ln key that accesses the S letter commands. Come on down and pick up sine hyperbolic inverse, not to be confused with regular sine inverse, right? And we want to evaluate 1 over radical 3. Minus, you want to evaluate it at 0. So you do again, second enter, reproduces the command. Just go back and plug in a 0. So we have roughly 0.55 minus 0, which will be 0. I'm sorry, which will be 0.55. How about the next example? How would you do this one? The integral of 1 over the square root of x squared minus 16. I would always think in steps. Like first step, can I apply regular good old U substitution? The answer is no, there is no x on the top, right? Because if you do have an x right over here, then can you use U substitution? Yes, like ubx squared minus 16, right? But we don't have that luxury. We don't have that x there. So we got to do something more out of the box here. So we ask ourselves, okay, can I use inverse sine, the regular inverse sine? Can I use that one? What would you need to have on the bottom for that one? It should be a squared minus x squared. It has to be in this format, the number minus the variable squared. We don't have that either. Then ask yourself, okay, maybe there's a list of formulas maybe on the back somewhere, because remember, I told you I would give you the formulas for these. Then you will go and search for the formulas, and hopefully you'll find then the correct one, which is which one? Right, number 2. This one, cosine hyperbolic inverse function, and you want x over a. In this case, it's going to be x over 4 plus c. We're done. Only the tangent has the 1 over a in front. If you look at the formulas, right, only the tangent one has a 1 over a, similar to the regular trig functions, right? Pardon, could you say that? Yeah. Yeah, sine has a plus, cosine has a minus, but they're both positive in their final answer. Only tangent has the 1 over a. Okay, how about this one? After, the hard part was getting the formulas. Once you have the formulas, you guys are used to, like applying a formula from inverse trig, etc. Applying them is really not so bad, as you can see. So let me bring back that formula here. So what do we get for this one? You need to be using this formula here, right? Again, once again, how did you know that you had to use an inverse hyperbolic function? Because if you don't need them, don't even think about them. First question, can you use U sub? Answer is no. Can you use a regular arctangent function? Can you use regular arctangent function here? No, but if you had a plus on the bottom, you could have used it, right? But not in this case. Then you say, okay, let me check what was those inverse hyperbolic functions again. Then we check those and say, okay, it matches this pattern here. And so it's going to be 1 over a, which is 1 over root 10, times tangent hyperbolic inverse function of x over root 10. If you had to evaluate these for any reason, remember where the commands are under your catalog. Okay, so I think I'm going to stop it with that, and I'm going to give you a few questions to work in your groups on the application process.